So hello all. Today I'm presenting Fabio Miranda. Fabio is a professor at University of Illinois at Chicago. But before getting to this position, Fabio started his computer science studies back in Brazil, where he got his bachelor's degree from Universidade Federal of Minas Gerais. And then Fabio flew to Rio de Janeiro to get his master's degree on PUC-Rio, where he worked on computer graphics. And then Fabio came to NYU to get his PhD degree, where he worked here at Vida Lab with Professor Claudio Silva, and also he worked on urban data analysis. So during his PhD, Fabio tackled lots of important problems of the cities, like trying to assess noise pollution and also try to quantify shadows of the city. Also, Fabio completed internships at Argonne National Labs, IBM Research, AT&T, Sandia. His work was featured at the New York Times, The Economist, Architecture Digest, Curbit, Flowing Data, and other venues. And right now, more recently, Fabio is working on how to leverage 3D data from the city to generate insights for domain experts. And besides that, not only like a promising researcher and a very good professor, Fabio is also a very good friend that I'm very pleased to have him here. So thank you, Fabio, for accepting this, to give this presentation. I'm sure it's gonna be awesome. Thank you.
Thank you, João, for the great presentation. Can I share my screen?
Yeah, I just made you a co-host, so you should be able to.
That's perfect. Can you see my screen?
Yes, we can.
Perfect. So thank you, João. Thank you, everyone, for the invitation. Yeah, my name is Fabio Miranda. I'm assistant professor at UIC. Just as João mentioned, I have a bachelor's in computer science from Federal University of Minas Gerais. Then I finished my master's in Rio, moved to the US in 2012, finished my PhD in 2018, advised by Professor Claudio Silva at Vida. Then I spent a couple of years as a postdoc at Vida/CUSP before becoming an assistant professor at UIC in 2021, October 2021. And so my research is really motivated about this wealth of data being generated. So for instance, more than 500 million tweets are produced each day. More than 4 terabytes of data is produced by connected cars. Almost 100 million photos and videos are shared on Instagram. So as Google's chief economist said way back in 2009, the ability to take data, to be able to understand it, to process it, to extract value from it, to visualize it, to communicate it, that's going to be hugely important skill in the next decades, because now we really have we have essentially free and ubiquitous data. So data can give us new insights about real world problems, such as the ones created by urbanization. For instance, by 2050, more than 90% of the world population will live in cities, and urbanization leads to several problems, such as related to housing, transportation, accessibility, among others. So my research really is at the intersection between computer graphics, visualization, data management, and machine learning. And I make contributions to these fields in order to propose new techniques and tools that allow domain experts to gain insights about data, ultimately creating a better understanding of the city. Example of experts that I have worked in the past include transportation specialists, acoustic researchers, urban behavior researchers, urban planners, and more recently, occupational therapists and physical therapists. So in order to tackle some of the problems created by urbanization, unfortunately, cities are creating new initiatives that are generating more and more data. Data from time series, such as from sensors deployed in around the city, to spatial temporal data, such as taxi pickups and drop-offs, social media data, to more recently building geometry data, such as the ones available by made available by OpenStreetMap, or by initiatives such as the ones from New York City. And also recently, we have access to image data at the street level, either by companies such as Google Street View or startups such as Camera. And all of this really goes to show the importance of smart cities, initiatives related to smart cities. And the number of smart city initiatives are only growing, showing the commitment not only from the government, but also from companies in deploying these projects and initiatives around the world. So my work is really about extracting knowledge out of this wealth of data. But unfortunately, this is not a straight path. It looks much more like this. In order to extract knowledge out of data, we really need to apply different techniques in this process from different fields. And in my research, I focus on data management, machine learning, visualization, and data structure. One way to think about my work is to think of the usual flow of data analytics. You have some sort of data, you can apply some transformation to this data. You might apply some data mining techniques in order to create a model of your data, do some parameter refining, and ultimately extracting knowledge out of your data. Another way to think about this is through visual analytics, where you create some sort of mapping between your data and the visualization. You add some user interaction in that visualization, and ultimately you extract some knowledge. And this, of course, is a loop. You can use your knowledge to better refine the data in your models and your visualization. And the interesting thing is that you can use visualization in order to visualize the models that you might create, or in order to better create the models out of your data. Here's a concrete example of a real system called Urban, which was motivated by real use cases from urban planners. In this particular example, I'm showing loading a data set of taxi pickups and drop-offs in New York City, and I'm aggregating this over different zip codes. I can also change the different parameters that I am visualizing, change the different data sets that I'm visualizing, and apply a series of constraints to this particular visualization. So for instance, if I want to just visualize the neighborhoods that have a certain amount of crime, or a certain amount of noise complaints, I can easily do this by simply brushing a parallel coordinate plot. So in this particular example, I am selecting neighborhoods that have a low amount of crime and a high amount of noise complaints, and a low amount of noise complaints. Through this visual analytics approach, you can also drill down to a particular neighborhood. So what I'm going to show next is the user selecting one particular neighborhood in the in downtown Manhattan, and further drilling down, considering now the building level data. So again, here the user is selecting Battery Park, and now visualizing the data not at the neighborhood level, but at the building level. And the user can now apply the same sort of filtering and visualization, but at the building level. So here's an example of the user applying some filtering and selecting the buildings that satisfy certain constraints. So in this talk, I will focus on three components of my work, or three thrusts of my work. First is understanding and modeling urban activities. The second is measuring the built environment and creating new data sets that can be leveraged by experts. And the last one is creating the tools to inform different urban communities. So the first one is understanding and modeling urban activities. As I mentioned, we have this wealth of data from the infrastructure, detailing the infrastructure of the city, the environmental condition of the city, social media, from the population of the city. And one of the big tasks that we had was, how can we leverage all of these data sets in order to compare different cities? And on top of that, how can we compare different scenarios so that we can compare cities during winter versus the city during summer, city during the weekday versus the city during the weekend. So in order to do this, we proposed this framework called Urban Pulse. And here's a simple example of how we can leverage spatial temporal data in order to see how the activity in a city is changing. So if we consider Flickr data, we can see that the city at 7 a.m. is completely different from the city at 11 a.m. We have all of these hotspots coming in and coming out as we move to, for instance, a late time, 7 p.m., we have new hotspots. So how can we, the goal here was, how can we leverage this data and use this to come up with a measurement of the activity in a city? In order to do this, we make use of computational topology, and we model the spatial temporal data as a set of scalar functions, and we use computational topology to extract interesting points or critical points in this scalar field. We first have one step, which is identifying the locations from interesting locations according to the topology of the scalar field. And we can leverage, we can model this data as a set of scalar functions over time, and we can use this to identify the points of maxima and also the locations that are prominent pulses, meaning that a location that's a high persistence of maxima in at least one time step, and a location that's a high persistence maxima in at least one resolution. After identifying these locations according to the topology of the scalar function, we can quantify these locations. So by quantifying these locations using the social media data, we have a signature that is data religious and allows us to rank the different locations in a city. So here is an example of a visual analytics tool that we built that leverages this type of data set to explore these different pulses and these different critical points extracted from the scalar field of the social media data. So in this particular example, the user is selecting a set of critical points and then visualizing, ranking these points according to the metric that we created, and then comparing what are the most similar points to the ones that I selected, but now in a different city. So for instance, San Francisco. So you can use this infrastructure to capture the most interesting points or the most interesting features in a city, and then use this to compare across different cities or across the same city, but under different constraints. So the city, what are the pulses of a city during winter versus the pulses of the city during summer, again, leveraging social media data. So in this particular paper, what we were interested, one of the case studies that we had was comparing different locations in a particular city, in this case, New York City. So in collaboration with Urban Planner, they selected 3 different spots in New York City that are typically classified together as being very similar. However, when we computed the pulses of these particular locations, we found out that they were completely different, which raises the question to precedents rated in different domains, such in this case, urban planning might not really match to how people are actually using the public spaces. In another work that we published last year or 2 years ago, we were interested in modeling commuting flows. Specifically, origin-destination flows can indicate how popular a given region is, and if there is a need for new infrastructure in that particular place. And this creates a very interesting scenario, because we can now leverage this in order to create alternate scenarios. So for instance, if you have a new high-tech industrial park being planned for a region in Brooklyn, from which regions would people commute to work in that particular neighborhood? How should we plan the support infrastructure to improve the commuting efficiency to that particular place? So we were really interested in answering questions such as this. After the construction of a mall, from what regions would people commute to reach that particular mall? How would this construction impact the flows of people to that particular neighborhood? And so the question that we wanted to answer here is, how can we model these flows considering the built environment information as to allow this type of scenario planning? And in order to do this, we leverage a multitude of data sets that describe the built environment of the city, the land use of the city, the transportation infrastructure of the city, and we model this as a graph that we propose we then propose a graph neural network that leverages this geographical contextual information to model the flow of people between different census tracts in different cities. So when we compared our approach with different state-of-the-art techniques, we found out that we were actually better than the state-of-the-art. And one of the interesting aspects of this work is that we can now leverage such a model to create this for scenario planning. So if you change certain built environment features in your city, how is that going to impact the flow of people to and from a particular neighborhood in your city? And this raises important questions related to the data availability and data quality that we are now investigating. So in a recently published paper, we applied this set of models, specifically the graph neural network model, but also Node2Vec and other models. And we assessed this model in the context of cities that might not be as data rich as New York City, for example. So in collaboration with a professor from Brazil, we applied the same model, but now to investigate scenario planning in Recife. And in this published paper, we had 2 case studies that really try to investigate how would the flows change if you modified the built environment of the city. So in one case study in the paper, we distributed 24 kilometers of cycle paths between different avenues in the city. And we evaluated how that would impact the flow of people. And in another case study, we simulated the construction of 13 towers on a historical site in the city. And through the modeling of the different flows, we can see how the impact of those proposed changes on the flow of people between the different census tracts. So the most interesting aspect in this line of work is that it allows us to perform these scenario plannings and modify the built environment and see how that would impact the flow of people to and from certain places in the city. So another thrust in my research is that I would like to highlight is measuring the built environment and creating new data sets to describe the built environment. So in order to better understand cities, we must consider different data sets to allow us to extract certain properties at different scales. From the human scale, such as what's happening at the street level, all the way to city scale. So the flows of people between different census tracts. So one of the particularly interesting example of this is shadow and shading. This information can be particularly useful to identify potential places that have a higher risk of black ice formation, but also to improve pedestrian level of comfort by identifying places with more shade during the summer. And this is particularly important given the recent boom in the construction of skyscrapers. And the shadow cast by these skyscrapers can not only impact vegetation growth, but also the well-being of people. And this has created several disputes between communities and developers, communities wanting to minimize the construction of these skyscrapers and developers wanting to build more and more skyscrapers. So in this recent work, we were really interested in quantifying the impact of shadows on public spaces. So here's a very concrete example of what I mean by quantifying shadows. This is a 2-hour time lapse in a neighborhood in New York City, and we identified here 3 different points: point A, point B, and point C. Point A is never under shadow during this 2-hour period. Point B is under shadow for half of the time, and point C is always in shadow during this 2-hour time frame. So we can consider that the accumulated shadow on point A was 0 minutes, the accumulated shadow on point B was 60 minutes, and the accumulated shadow on point C was 120 minutes. So our objectives in this line of work was to support the comprehensive and interactive analysis of city-scale shadows. And more importantly, we wanted to enable the accumulation of shadows through large period of time. So again, we wanted to enable the analysis considering large periods of time, such as months, so that we wanted to compare the amount of shadow in Central Park, for instance, during summer, versus the amount of shadow in Central Park during winter. And we wanted to support different analysis measures as to enable the computation of the difference between shade and shadow, As I mentioned, shade can be positive during hot summers, but shadow can be negative during cold winters. And we also wanted to compute the contribution of individual buildings to the shadow cast on public spaces. We do this through this technique that we called shadow chrome maps. That's nothing more than a 3D texture where each 2D slice of this 3D texture will store the shadow information at that particular time frame. So if we consider in this slide the shadows cast by point S at time step T1, for instance, 12 p.m., and at time step T2, for instance, 12 p.m., being P1 and P2, the values between P1 and T1 and T2 can be linearly interpolated and then stored in their corresponding 2D slices in this 3D texture. In this paper, we also proposed an inverse chrome maps, which is a ray tracing based technique, more accurate than shadow chrome maps, and used for detailed shadow analysis. And it follows the same principle of linear interpolation. So given 2 points that given a point that's casting shadow at different time steps, we simply linearly interpolate between these 2 points. Here's a concrete example of shadow chrome maps. Here is for Chicago. The redder the shade, the more shadow you have in that particular spot through an accumulation period of 6 hours in this particular case. Using this technique, these 2 techniques, we proposed this tool called Shadow Profiler that we made available to architects and urban planners. And this allows them, the tool allows them to quantify shadows at different time intervals. So for instance, on the left image here, what we have is the accumulated shadow for a period of 8 hours, for a period of 25 days, and 8 hours in each one of those days. And on top of that, you can also see how much shadow was contributed by each individual buildings. So by each individual building. So the darker the blue, the more shadow that particular building contributed to the shadow cast on Central Park, on South Central Park. And another interesting feature of this tool was that it allows for scenario planning. So on the right image, what we can see is a particular building was replaced by with a new building in shades of blue and shades of red. What we can see is how much shadow would be removed or how much shadow would be added to the environment if that particular building was added, replacing a different building. So in this particular example here, what we see is that the building in purple would add the shadow in shades of red, but would remove the shadow in shades of blue. So in the paper, we have 3 different use cases. I would just like to highlight one of them. And in this use case, the domain experts, the architects and urban planners, they were interested in the analysis of 2 different scenarios. Both of them with buildings with the same total floor area. In scenario 1, we have lean and tall buildings. In scenario 2, we have bulky and short buildings. And what they wanted to analyze here was how much shadow would be added by these 2 different scenarios. Here's an example of the tool in action. So what we see here is the domain expert adding the different buildings in New York City, and then accumulating the shadow of these buildings for a period of 4 hours. So in shades of red, what we see is how much shadow would be added by those 3 particular new buildings, and only by the shadow added by those 3 particular buildings. Here's the comparison between the result of this computation, comparing these different scenarios. On the left, we have the shadow added by the lean and tall buildings. On the right side, we have the shadow added by the short and bulky buildings. And it was interesting to notice that the short and bulky buildings would actually add more shadow to the park when compared to scenario 1, which is the tall and lean buildings. So in collaboration with the New York Times, we made this data available to them, and you can go to, using this visualization tool that the New York Times created, you can go to any place in New York City and see how much shadow would be added to, how much shadow is being cast in that particular spot through the 4 seasons of the year. So in this particular example here, we can see that in this particular spot would get 0 minutes of sunlight throughout the entire winter. And exploring this shadow data computed by us through the New York Times web visualization tool, we are able to see the accumulated shadow at different locations in New York City, such as the Yankee Stadium, Financial District, Broadway Avenue. And interestingly, what we found out was that during winter, several streets between avenues in New York City will have no direct sunlight during the entire year. In fact, the majority of streets between avenues in Manhattan will have no direct sunlight through the entire winter. This research was later picked up by different media outlets such as Flowing Data, Architects Newspaper, Technology, etc. We extended this to other cities in the US. So we made available this data for Chicago, Washington, D.C., LA, Boston, and you can pretty much, we also created a visualization interface very similar to the one in the New York Times, where you can go to any place in these 4 different cities and assess how much shadow is going to be cast in different spots in the city throughout the different seasons of the year. Another interesting feature that we were interested in was surface material, specifically sidewalk surface material. This is crucial in terms of safety and accessibility. It is of great importance to wheelchair users, since different textures create different levels of friction that can become potential hazard, but also from an environmental aspect, the material of surface material can impact urban heat island, stormwater management, combined with overflow. So in this other line of work, we were really interested in creating data sets with a representation of the different materials at sidewalk level. So we proposed this framework called city surfaces, which is a computer vision framework for the semantic segmentation of sidewalk material, leveraging street level images. It uses an active learning approach, and what it allows you to do is to feed any type of street level image, and the model, the framework will output that particular image segmented according to the material of the sidewalk. So rather than just segmenting, considering very high level features such as sidewalk, facade, road, this model, this framework allows you to segment considering the material of that of the different materials of the sidewalk. For instance, concrete, bricks, asphalt, granite, etc., etc. In this work, we consider 8 different types of materials, but it's extensible enough that you can add more materials. And the interesting aspect of this, or the most interesting aspect of this, is that we can use this to compute the distribution of materials throughout different cities. So in this image, you can see the city scale maps showing the dominant material per segment of these 3 different cities: Chicago, Washington, D.C., and Brooklyn. Again, we made this data available on GitHub, and on top of the model, which is also available, we made available a shapefile with the distribution of the different materials in the city, different sidewalk materials in the city. And one very interesting aspect of this is that now we can leverage this multitude of data in order to tackle very concrete challenges, such as outdoor risk of falling. A very challenging task is the detection of black ice. And so in our current work, we are leveraging not only sidewalk material, but also shade information, temperature, reported incidents from the Illinois Department of Health to create outdoor risk fall models, or what are the places in a city that are more likely to cause falls, So in the last thrust that I would like to highlight is how can we create the tools to inform urban communities. As I briefly mentioned, we have more and more data about the different conditions of the urban environment. And a very important aspect of my work is how can we make sure that the urban experts have the tools and the capabilities to tackle their problems, leveraging this wealth of data. One particular work that I would like to highlight here is accessibility. Accessibility has become a very important topic throughout different cities. So important that it has led to different lawsuits against the city of New York over the poor quality of the sidewalks, and led to New York agreeing to install tactiles on all intersections. So in this line of work, I really want to enable researchers and various stakeholders to combine different data sets and find new patterns to answer the questions or solve existing problems. One recent paper was this one called Urban Mosaic, that leverages a multitude of data sets from street level images, material data, shade information, building geometries, 3-in-1 complaints to assess questions of accessibility. One of the data sets that we leverage is this street level images, such as Google Street View, where we have images from the different sides of a car going through the city. But while Google Street View is spatially dense, it is temporally sparse, meaning that you have very few pictures throughout the entire year. In this tool, we leverage a temporally dense street-level image. This dataset has more than 7.7 million images, more than 4 terabytes worth of data, and allows us to see the evolution of the city throughout a larger period, a larger time frame. So in this particular example, we can see from the initial constructions of a building all the way to the opening of a store. So in this line of work, we wanted to support this interactive analysis of the city at the micro scale over potentially geographically distant locations. We wanted to do this in order to enable the comparison of urban fabric in different regions and the assessment of features in the built environment, ultimately to answer questions of walkability and accessibility. Here's an example of this tool in action. What we have here is the user selecting images from a neighborhood in Brooklyn, and then the user can select for images that are similar to that particular one. So he's selecting a architectural feature, the windows of a particular building having certain shape, and then the user can find for similar images throughout the entire data set. And of interest here is that then the user can see what are the regions in the city that are more likely to have that particular architectural feature, meaning the windows in that particular shape. We also use this to assess the installation of tactile pavings. So in one case study in the paper, we assessed the installation of tactiles in one block of the city in leveraging this interesting aspect of the data, meaning that it's temporally dense. We can go back in time to assess how that particular tactile looked like during after a heavy rainfall. And also we could see how that particular tactile, the state of that particular tactile in the future months. Another interesting aspect of this tool is that allows you to assess the built environment under different weather conditions for the assessment of hazard for older adults. So in this particular case study, what we have is the user selecting one particular spot in the city that might have a higher concentration of older adults, and then using the fact that this is a temporally dense data set to assess how that particular corner in the street would look like during heavy snow and after a day of heavy snow. So this can be particularly useful to assess the condition of the built environment, not only during perfect conditions, such as a sunny day, but also through a day of heavy snow, after a day of heavy snow, which talks to the necessity in the creation of these types of data sets, temporally dense data sets. So another research project that I would like to highlight is one motivated by this, the problem of air pollution in Chicago. Chicago ranks among the top 5 worst cities in the US for air pollution near public schools. And what we found through this research project over the past year is that air pollution disproportionately impacts underrepresented communities in Chicago. And so in collaboration with the Department of Civil Engineering, the School of Public Health, and the Department of Urban Planning, we wanted to understand and increase community participation in environment justice. So Over the past 6 months, we have been developing a series of dashboards built in very close collaboration with communities from Chicago. We had a period of 6-month interaction with these communities, which our goal here was to assess the cumulative impact of environmental hazards, meaning industrial roads burden, rail yard burden, brownfield burden, and we created a series of dashboards, 3 dashboards that leverages a different that leverages different data sets in order to assess questions related to environmental justice. And the most important aspect of this work is that all of this set of dashboards, while simple and were quite simple, they were built in very close collaboration with this set of communities in the south side of Chicago. And the importance of tackling pollution problems through the lenses of environmental justice is really highlighted by the media mentions that we have been getting over the past few months. So even though these dashboards that we created in collaboration with the community were simple, we were featuring a number of media outlets, from local media outlets such as McKinney Park News to the Chicago Tribune, Univision Chicago, which really stresses the need to create tools to inform and engage the community in questions related to environmental justice and air pollution. So the dashboards that we have been creating over the past few months are now being used by the community to engage with stakeholders and to make sure that the different city stakeholders, aldermen, congressmen, congresswomen, are aware of the problems faced by this population in Chicago. All of this work is being done under this project called PRESUR, Planning a Resilient and Equitable State Using Real-Time Data, which is a interdisciplinary team from UIC, UIUC, University of Chicago, that tries to establish this center to address problems of equity and resilience in Illinois through the combination of fine-scale urban data science, integrative urban predictive models, urban system science, and community participation. So at the foundation of all of this effort is this very strong link with a community in Chicago and understanding their problems, but also making sure that our research output goes to tackle and goes to gives them agency in order in how they conduct the interactions with the different stakeholders in the city. One of nice outcome of this project as well is that we are in the initial stages of deploying a K-12 initiative in this community together with the Dyson Foundation, and creating a set of courses that allow K-12 kids to engage with STEM research and to build their own air pollution models or their own air pollution devices and measure the pollution, the air pollution in their own homes. Another aspect of this work is not only creating more equitable communities, but also creating more resilient communities. Specifically, in the last 20 years, climate-related disasters caused the death of more than 1.23 million people. There has been a staggering rise in the number of landslides, droughts, and wildfires. And an important aspect in order to tackle these problems is to move beyond this idea of treating cities as just flatlands. So in our current work, we want to move beyond this idea of city as flatlands and really leverage this 3D aspect of cities. Using the same sort of approach of modeling in data generation and creating the tools to inform urban communities. So concretely, what we are doing is, in this line of work, is creating a vulnerability index to guide resource deployment for disasters such as landfall and rainfall. We're also leveraging 3D point cloud data to create new measurements of accessibility, and also creating new glyphs and visualizations for the visualization of multivariate data specifically on building surfaces, such as shadow information on building surfaces. So that's all. If you're interested in taking a look at my papers, tools, and data, they are all available at my website. Thank you very much.
Thank you. That was really
Thank you so much.
amazing.
Thank you.
So now we're going to turn to Q&A. And so can you please use the mechanical hand function to signal you have a question. Yeah.
Okay, so thanks, Fabio, for the presentation. And as we saw in your presentation, your work deals with a lot of domain experts, right? Architects, social scientists, for example, occupational therapists, as you said. So I was wondering, what is the most difficult part of this process of communicating your ideas before building the tool? And how is this process of trying to get the requisites for such a tool from them? Do they understand like the computer science way of speak well? I mean, do you have to adapt your communication? I mean, what are the difficulties through this process?
Yeah, I guess that's the most difficult aspect, which is making sure that they don't treat you as just a software developer, but as a researcher, right? And I guess the most important part there is making sure that you establish collaborations with people that do understand this and treat you as someone that's trying to help them, trying to help their research, but also at the same time doing your own research, right? So I don't have a set of rules or guidelines for that, but that's the most challenging aspect, which is making sure that they understand you as a researcher and a person that also needs to publish papers in your own domain, and not someone that will just apply models and methods to their problem, but not getting papers in your domain. So I don't have a guideline for that. I can only say that that's a very tough challenge. But once you do find the expert that has this angle, that approaches you from a research perspective rather than a software engineer perspective, the most important part is to make sure that you keep engaging with that domain expert and leverage that domain expert in the best way that you can, right? Like creating collaborations is not the easiest thing in the world, but once there is that opportunity to create that collaboration, to establish that collaboration, it's important to not drop the ball in terms of always keep that person engaged because that person is fundamental to your research. I mean, I'm not sure if I answered the question, but I would say that it's difficult. And once you do find that person, make sure that that person is engaged in your research and in your problems.
Yeah, I guess it answers. Thanks.
I'm going to take moderator's prerogative and ask my own question. Again, this is a really awesome presentation. I learned a lot from it, and you kind of touched on this towards the end of the presentation, and feel free to go back to it. I'm a scholar of inequality, and I was kind of thinking about what's the inequality story here, and in particular, I was thinking about Ruha Benjamin and Kathy O'Neill's work on the implications of big data for inequality, and thinking about this from both the data collection side. So how does inequality form the kind of data that you're able to collect, and then from the developing and applying these tools side. So how can these tools be kind of used to, or rather kind of made accessible to, not people who are not urban planners or skyscraper developers?
So yeah, I mean, I can answer that from both sides. So from the data acquisition and the tool deployment aspect of it. So the data acquisition, especially after this collaboration with this community in Chicago, we really found that there is this need to capture data in underserved communities. So throughout this 6-month period, one thing that we really found is that this particular community is being severely impacted by different, from multiple angles. So they are being impacted by the number of brownfields in that community the number is way higher than in different communities in Chicago. The number of facilities, TRI facilities in that particular toxic releasing inventory facilities in that particular community is way higher than in the rest of Chicago. And they also have a transportation hub, I think 3 transportation hubs in that particular community. So they're being impacted by brownfields, TRI facilities, and transportation hubs. And we found out that there was really no initiative to capture data, air pollution data in that particular facility. So we right now what we are doing is making sure that we do have the capabilities to measure the air pollution quality in that community through sensor deployment. So that's going on, and that's going on also from 2 angles. So we are deploying our own sensors, high quality sensors, to measure air pollution in that particular community. We're also collaborating with Microsoft. They have their own high density network of sensors in Chicago. We're collaborating with them to specify the places that they should be collecting data for that particular community. So that hopefully solves the problem of data collection and data acquisition for that particular community. And the third one, and the other aspect is creating the tools that give agency to that community. So through this 6-month collaboration with them, we really found out that they are really engaged by this easy to use, intuitive dashboards. So we created 3 dashboards over this period of 6 months. And out of all of my research, those were the most widely used visualization tools that I have ever created. So the other day I went to see the statistics of these tools, and they have been accessed more than 3,000 times. So even though like and that's way more than this domain tools for the domain experts. And so even though they are very simple, intuitive, they really go to tackle this problem of how can you make sure that the community is aware of the air pollution problems in their neighborhood. And the interesting aspect that came out of this in terms of giving agency to the community is that they are now pressuring the government to make sure that some rezoning takes place in that particular community, which raises interesting problems as well, because the majority of the community works in these facilities that are polluting their own community. So how can you make sure that you have a zoning plan that tries to alleviate the burden on that community, but at the same time you don't you have the mechanism that the jobs will not move to a different location of the city, and you leave that particular community without jobs. So equalizing this is something that this project tries to tackle. That's at the core of this project. That's why we have people from urban planning, School of Public Health, from all of these three universities, because it's not an easy problem, and it's not just through sensor deployment that we're going to solve this, and it's also not through dashboard building that we're going to solve this. So I think that at the core of this problem is this nice aspect of community engagement and making sure that fundamentally we give them agency to engage with the stakeholders, to engage with government officials, in order for the government officials to know that, yes, this is a community that's being severely, that's being impacted by pollution in a disproportionate way. So, yeah, I guess that my takeaway here is that we're trying to do research that fundamentally is driven by the needs of this community in terms of sensor deployment, but also in terms of creating the tools that allow them to engage with the stakeholders and to engage with the government stakeholders. So did I answer your question?
Yeah, thank you. Other questions for Fabio?
Yeah, I guess I have another question. So, as you mentioned, you have like this tool that was widely accessed by people, right?
Mm-hmm.
But when you're developing these tools in academia, especially, after sometimes you have to spend some time maintaining this tool, writing new code, making sure the infrastructure is running. And that's always it's very challenging in academia, since, I mean, we spend most of our time like doing research, and we don't have much time to do like this engineering part of the research. So how do you see, I mean, do you have any thoughts on how to solve this gap, how to bridge this gap between having a nice idea that helps people, but also at the same time building a system that's like robust and it's gonna allow for people to use and keep it running for a long time, years, For example, so have you ever thought about this? I mean, is that a problem on your group? I mean, is there something that you faced in the past? I mean, what are your thoughts about this
So
gap between?
yeah, so I had the opportunity to both create tools that were not massively deployed to users, and now creating tools that are being deployed to users and non-CS users, right? So I guess that my advice would be to start from, if you start if you have an approach that from the start considers that the tool needs to be made widely available to users, you throughout the development of the tool, you will if you keep that in the back of your head throughout the development of the tool, you will make sure that you put in place certain features that will make sure that the tool has some sustainability in it, right? So, and I guess that always keep in the back of your head that yes, this needs to be sustainable and this needs to be made available to a wide set of users. If you approach the problem from this angle, you start removing certain features that will either create problems for the user, or that you'll be very hard to maintain. So you start removing those features, and you start also appreciating another aspect of this research, which is the interaction with the user, right? So there's a lot of nice insights that you can gain from this whole process of building the tool. Like, I guess that rather than thinking that the paper is only the tool, the final product, the tool is the final product that's going to be reported in the paper, then the whole process should be something that's reported in the paper, right? And if you approach this problem from this angle, rather than if you approach the problem from this angle, it becomes much easier to, one, considering that any interaction will be something that's worthwhile to put in the paper, and to kind of remove features that will not add anything to the user, and will just make it harder for you to sustain the tool. So I'll say, no, if you approach from this beginning that the tool, as a requirement of the tool needs to be available to a wide audience, right? This is a requirement of the tool. If you approach from this angle, and not just as it would be nice if the tool is available to the, if you approach that it's a requirement and it needs to be done, you start dropping features, you start reporting the interaction as a contribution in the paper, and the whole frame of mind that you work will be slightly different, and that will help the whole process of building the tool. Did I answer your question?
Yes, thank you.
Vivian.
Thank you so much for this very fascinating talk. Wanted to follow up on what Jacob asked in terms of equality and then the data collection. You mentioned having engaged government officials. I was curious if you could talk more about if there have been next steps with the government officials.
Yeah.
For example, if they have adopted policy changes based on your findings, and what is the process like working with them?
Yeah, so this is an ongoing process. What has happened after we have released specifically the last dashboard, we made two presentations to an alderman in Chicago, and I've got he runs the commission, the environmental commission in the city of Chicago, and so we they are aware of this problem in this particular community, but it's not an easy problem to deal with. And even though we raised the problem and we're starting to give the tools and the agents to this community, and we're starting to engage with the politicians, it's not a straightforward problem to solve, because there's other factors, economical factors involved in this problem, and we're not naive to think that dashboards and models will solve this very complex problem. So our goals is to initial goals is to start the communication, establish the communication channel between the community and the governmental officials, right? And this channel is in place. So we made we had two meetings with this alderman in Chicago. He's aware of the problems facing this community. So we started this process, but it is a complex problem to solve. There are economical factors, there are social factors involved in this, and we are happy that we are giving them the tools to engage with the officials, but we're also aware that it's a very complex problem, deals with economical issues, and so it's a start. I'm not saying that we are going to solve the problem, but we are hopefully building towards something that can solve the problem. By establishing this communication between, so I was very happy that we were able to establish this communication between the community and the alderman in Chicago, and that was a very concrete thing that came out of this research project, right? And also the other nice things that I like to think of this as creating the next generation of STEM researchers, right? So one of the other nice aspects of this research project is that we're engaging with schools in this community and starting to think of plans to make sure that the school kids are aware of the problems facing their community. So we certainly won't solve this problem in 5 years, 10 years, but maybe future generations will be able to solve by knowing that, yes, that community is being impacted in a disproportionate way. And disproportion is the key word here. Like, there is no way to everyone is going to be impacted by air pollution, but the unfortunate thing is that that community is being disproportionately impacted by air pollution.
Thank you.
Jocelyn? Oh, sorry.
Hi, yes, thank you. Sorry, I can't be on camera right now. But this is super interesting work. And one thing that I keep sort of wondering about is sort of the limitations of available data sets. And I think, the example that you're giving of the community in Chicago and engaging folks to actually collect their own data in terms of air pollution, that's an example of overcoming a data limitation. But I'm kind of curious on a broader level, other examples of situations in which even like a complex data set, or not a complex, but a vast data set like Google Street View, for example, is not giving you quite what you want to measure. I'm just kind of curious what your process is for kind of dealing with that issue broadly, and kind of a more hypothetical question, like, is there a data set that you wish existed that, sort of a problem that you want to research, that you want to tackle, but without a data set currently that you would love to see somehow brought into existence? And do you have any sort of ideas about how that might happen?
Yeah, so I am very much interested in part of my previous work was leveraging image data in order to extract certain features out of certain urban features, right? Either the material of sidewalks or the installation of tactiles. But no, of course, you have limitations when it comes to image data. Image data you might have a car that stopped right in front of the camera. You might not be an ideal weather condition, etc. So you of course have limitations when it comes to image data. So one of the interesting things that we are pursuing right now is leveraging LiDAR point cloud data. Specifically, there are interesting features that we can extract from point cloud data that we would never be able to extract from image data. So for instance, the height of curbs on sidewalks. That's impossible to extract from image data, but that can be extracted from point cloud data. So I think that leveraging point cloud data opens this great set of opportunities for measuring the city. That's one. The other problem is, it's very easy to do it's easier to do urban related research if you're in a city like New York or Chicago or LA. And in working in collaboration with with professors from Brazil, we found out that it's almost impossible to do this type of work in other countries, right? Specifically Brazil. So how can we create the same environment that we have here and replicate this in countries such as Brazil? Specifically, what are the network of sensors, what are the techniques that we need to employ to capture data at the level that we have right now in New York City, in Chicago? We can't leverage OpenStreetMap in Brazil, for instance. Is there a way that we can generate the data at the same resolution that we have in New York City, in Chicago, but this time for Brazil? So one of the things that we are currently pursuing is putting in place the right crowdsourcing initiatives to generate data from places that you might not have data. And I think that it's one of the most interesting aspects here is how do you use data, how can you extract data? So for instance, you might not have building information in Brazil, but you do have a very nice coverage from Google Street View in Brazil. Can we leverage Google Street View in order to generate building geometries in cities from Brazil? So I guess the nice opportunity is leveraging other source of data where you might have a good coverage in order to generate other data sets, for instance, building geometry. So realizing these nice opportunities to leverage data sets in order to generate new data sets, I think it's something very much interesting and something that we are currently pursuing. So I don't know if I answered your question, but that's the kind of the gist of it.
Great, thank you.
All right, Georgie, sorry.
Hi, so thank you very much for your presentation. It was really super interesting. And one of the things that I thought was very interesting was that slide closer to the end where you talked about moving beyond the flatland. So maybe you could talk a little bit more about how 3D visualization of the urban space helps your work and what are the challenges involved in that. And also looking at your website, I noticed that you recently explored also virtual reality as a way of exploring the urban space. And I'd like to know what is your initial insight on what contribution can immersive analytics, for example, have for urban data exploration?
Yeah, so in terms of so there are two lines of work in this regard related to VR / 3D built-in data. The first one is, what are the best ways to display information on building surfaces, right? You might have this specifically, now you have this wealth of data generated at the building surface level. So shadow is one example of that. We have information on the surface of buildings. Earthquake simulation is another example of that. View impact is another example of that. So it's not data restricted to the flat land, to the environment, but is data that has this very nice component that, and it's intrinsic to urban environments, which is this 3D aspect of urban environments. In this line of work, we're investigating what are the best ways to visualize this 3D data, considering that you might have occlusion, you might have multivariate data, temporal data, etc. So what are the best ways to visualize this on building surface? So in this ongoing work, one of the things that we are doing is trying different visualization metaphors on building surfaces. So I highlighted this on the right side here. So we have different visualization metaphors to visualize multivariate temporal data on building surfaces. And now we're measuring what are the best ways to visualize this, considering that you're moving one dimension up. You're not on, right now you're not restricted to the surface, but now your data is at the surface level. So we are trying different metaphors, different widgets, and measuring from a user study perspective, what are the best metaphors in order to visualize surface data. And one of the main inspirations of this is oil reservoir visualization, right? So this is very closely related to oil reservoir visualization in the sense that, well, in that domain, they are also visualizing data that happens at the surface level. So we are modifying several of these techniques that have been previously proposed to oil reservoir visualization, but now to the urban 3D domain. So that's one line. The other line, in that's not VR related, but this can be applied to any type of 3D visualization, whether it's a cave, whether it's a VR, whether it's a desktop visualization. So that's one. The other one is, one of the major problems in virtual reality in urban environments is how do you navigate in the city, considering that occlusion is a big problem. So how do you navigate in the city? We kind of scratch the surface of this problem in the Urban Rama paper, but it's still very much not intuitive to navigate in cities. Specifically that, most of the navigation VR schemes today, they don't for urban environments, they don't take into account that you want to perform certain analytical tasks when visualizing data. So can we create navigation schemes, VR navigation schemes that take into consideration the data that's being displayed at the surface of these buildings and guide the user in the sense of the best positions in which he or she needs to navigate to in order to visualize the data. So we are in this ongoing work as well, approaching this problem as can we leverage the data that's being displayed at surface level to reduce the number of points that the user needs to navigate to in order to have some coverage of the data set. So yeah, that's kind of broad picture of what we are currently working on in terms of VR and 3D visualization. Does it kind of make sense?
Oh yeah, definitely. Very interesting research directions. I'm very curious to see what comes out of it. Thank you very much.
Thank you.
I want to thank Fabio once more for this great presentation. We're going to take a short break now and come back at 1:15 for the private session with the Urban Seminar members. So can everyone please join me once again in thanking Fabio for a great presentation. And thank you all for coming.